Good day, everyone. Welcome to Richfield Hybrid Learning Program. My name is Silas Toperesu, and I'm your lecturer for Mathematics 512 module. Today, we're going to look at our syllabus topic 5, lecture 2 for integration. On learning outcomes, after the study of this topic, you'll be able to demonstrate your understanding on how to integrate any function or expression. You'll also be able to demonstrate your understanding on how we differentiate, how we integrate definite integral and indefinite integral, and how to find the area under the curve using definite integrals. And you also have an understanding on how to integrate an expression or function using an integration by part method. In addition to that, you also have a know-how and knowledge on how to integrate any function such as exponents function, logarithmic functions, and trigonometrical functions using rules of integration. Let's look at the definite integrals. Definite integrals are used when we calculate the area under the curve or area enclosed by two functions. The general notation of area under the curve is given by the integral of upper limit b and lower limit b of fx dx. This is known as the definite integral of an fx function. We define the definite integral of a function fx as the integral of fx dx with the upper limit of b and the lower limit of a, which is also giving us the same results when we substitute the value of b in our function and subtract with the substitution of value of a, which is the lower function in our function, where the derivative of fx is equal to fx. The numbers which is a and b are called lower limit and upper limit respectively. So the upper limit is the one that is on upper part of our integral sign, and the lower limit is the value that is on our lower part of our integral sign. Here are some properties of definite integrals. The first property states that if we have got the integral of fx dx with the lower limit of a and upper limit of b is the same, the solution of this integral is the same as the integral, the negative integral of fx dx with our lower limit considered as an upper limit, which is a, and then our upper limit considered as a lower limit, which is b. The second property states that if we've got an integral of an fx dx with a lower limit of a and an upper limit of b plus the integral of fx dx with a lower limit of b and an upper limit of c, where b is an intermediate value between the range or interval of a to c. The solution of this addition is the same as the integral of fx dx with a lower limit of a and an upper limit of c. The third property states that if we have got a constant, an integral of a constant multiplied to our function, let's say we have got an integral of k fx dx with a lower limit of a and an upper limit of b, the solution of this integral is the same as k, which are our constant, times the integral of fx dx with a lower limit of a and an upper limit of b. So we take the constant outside, then we find the integral of fx. So the solution of this integral is the same as the first solution, which is on our left side. So the fourth property states that if we have got two functions that are subtracted or added on each other, and we are finding the integral of it with the lower limit of a and the lower limit of b, the solution of these two functions with the difference or addition is the same as finding their integral separately. So we find the integral of fx with a lower limit of a and upper limit of b in terms of dx, and then we add or subtract with the integral of gx with a lower limit of a and an upper limit of b dx. Let's look at some examples of solving definite integrals. Our first example states that evaluate integral of 8x dx, which have got an upper limit of 5 and a lower limit of 2. So when we're finding the solution of such an integral, which is definite, we need to integrate 8x. When we integrate 8x, we look at the power of x, which is the power 1. So we add 1 on the power. Then when we add 1, we're going to get 2, and then we divide with the total power of our variable x. So we end up having 8 divided by 2x to the power 2 as our result. And now we substitute in place of x, we substitute our upper limit. And when we substitute, we subtract with the substitution of a lower limit. So we end up having 5 squared, which is our upper limit. We put in place of x, we're going to get 5 squared minus the substitution of lower limit, which is 2. We end up having 2 to the power 2. 2, and it gives us 5 to the power 2 minus 2 to the power 2, which becomes 25 minus 4, which gives us 21. Now we say 4 times 21, which gives us 84 is our definite value of this integral of 8x dx with an upper limit of 5 and a lower limit of 2. Here is our second example, which states that evaluate integral of 6x squared minus 5x plus 2 dx with an upper limit of 1 and a lower limit of minus 3. So when we find a solution integral of such an expression, we need to integrate term by term. So when we integrate our first term, which is 6x squared, we add 1 on a power and then we divide by the total power. So we end up having 6x to the power 2 plus 1 divided by 2 plus 1, which is our total power, and the second one, which is minus 5x, we add also 1, we are going to, and we end up having minus 5 x to the power 1 plus 1 divided by the total power, which is 1 plus 1. Then the third one, which is integration of a constant, which is 2, we're going to add also 1 on x, and because we have got x to the power 0, so end up having 2x to the power 0 plus 1 as our result with an upper limit of 1 and minus 3 is our lower limit. Now we solve this one, we end up having our final result as 2x cubed minus 5 over 2x squared plus 2x with an upper limit of 1 and a lower limit of minus 3. And now we substitute our upper limit in our expression. When we substitute our upper limit, we are going to substitute in place of x, we are putting our upper limit, which is 1. So end up having 2 times 1 cubed minus 5 over 2 times 1 squared plus 2 times 1. Then we substitute also, we say minus the substitution of a lower limit in the same expression. So we end up having 2 times minus 3 in place of x, which becomes minus 3 cubed minus 5 over 2. Then we substitute in place of x squared to substitute minus 3. Then it's going to be minus 3 squared, then plus 2 times minus 3. So when we solve this expression, we're going to have on our left side, we're going to have 2 times 1 cubed is going to give us 2 minus 5 over 2 plus 2 minus, when we are solving the substitution with the lower limit, we're going to get minus 54 minus 45 over 2 minus 6. So when we solve 2 minus 5 over 2 plus 2 is going to give us 3 over 2. When we solve minus 54 minus 45 over 2 minus 6 is going to give us minus 165 over 2. Now a minus and a minus, it gives us a positive. So we end up having 2 over 3 plus 165 over 2, which gives us a final result of 84. Here is our third example, which says evaluate integral of sine x dx with an upper limit of 2 pi and lower limit of pi over 3. So when we are finding the solution of a trigonometrical function, which is sine x in terms of pi, we need to know that a pi is cos 180 degrees. So when we're finding the integral of such a trigonometrical, we need to know, using the trigonometrical rules, what is the integral of sine x. So the integral of sine x using the trigonometrical rules of integration, the integral of sine x is equals to minus cos x. So now once you get the integral of sine x, which is our trigonometrical function, minus cos x, we have an upper limit which is 2 pi and a lower limit which is pi over 3. We substitute in place of x is put 2 pi. 2 pi, when we put 2 pi now, we're going to have minus cos 2 pi minus substitution of a lower limit. Now we have got a negative cos pi over 3, and a negative is going to, when we find the first one, which is minus cos 2 pi, minus cos 2 pi is going to be minus 1. It gives us minus 1 when you solve this one, which is a minus cos 2 pi, it gives us minus 1. Then minus cos pi over 3, it gives us minus half. So now we've got a minus 1 minus half, and minus becomes positive. So end up having minus 1 plus half, which gives us our final result as minus half. Let's look at calculation of area using definite integral. Here we have got an example that says find the area under the curve y is equals to x squared between x is equals to 1 and x equals to 3. So the question is asking for the area covered between x-axis and the graph of y is equals to x. So when you draw the graph of y-axis, you are going to have a graph like this, which touches the x and y axis at 0, where x equals 0 and y equals 0. And now we need the area, which is the one that is shaded here, which is between x is equals to 1 and x is equals to 3. So x is equals to 1 is going to be our lower limit, and x is equals to 3 is going to be our upper limit in our expression. So now we need to integrate our function for this graph, which is the function saying y is equals to x squared. So we integrate in terms of x. So we're going to integrate the function that is integral of x squared dx in with the upper limit of x is equals to 1 and the lower limit of 1. When you integrate x squared, you are going to add 1 on x. So end up having x squared plus 1 divided by the total power, which is 2 plus 1, with the upper limit of 3 and 1. So we're going to have the final integration result as 1 over 3x cubed. And now substitute our upper limit, which is 3. When you substitute our upper limit in place of x, we're going to get 1/3 x cubed minus the substitution of a lower limit in the same result, which is going to give us 1/3 times 1 to the power 3. And when we solve, we're going to get 27 over 3 minus 1/3, which gives us our final result is 26 over 3 square units as an area covered between the graph of y is equals to x squared and the x equals to 1 and x equals to 3. Our second example for finding the area of a graph using the definite integral is the question stated that find the area between the curve y is equals to x squared plus 4x and the x-axis from x equals to minus 2 to x is equals to 2. So when we draw the graph of y is equals to x squared plus 4x, you are going to see that our graph cuts the x-axis at minus 4 and it cuts the x-axis at x is equals to 0. So the area that we need the area that is below the x-axis, which is from x is equals to minus 2 to x is equals to 0. And then we've got another area that is above x-axis, which is where x is equals to 0 up to x is equals to 2. So we have got two areas, one area that is below the x-axis and the other area that is covered above the x-axis. So since these x areas are separate, we need to separate our integral and to separate our limits. So we need to find the area from the range minus 2 to 0, and we need also to find the area from range 0 up to 2, since these areas are in different sides of x-axis. That's why we have to separate them. So we label them as area 1 and area 2. So when we find the area 1 and area 1, we say the integral of our function, which is x squared plus 4x dx, with the range of our upper limit is 0 and lower limit minus 2, plus the integral of our upper area, which is area 2, which have got the upper limit of 2 and the lower limit of 0. So we have, which is of the same function. So we say the integral of x squared plus 4x dx with upper limit of 2 and the lower limit of 0. Now when we are solving for area 1, we are going to integrate our expression of x squared plus 4x. When we are integrating x to the power 2, we add 1 on the power, then we divide by the total power. So we end up having x cubed divided by 3 plus, when we're integrating 4x, we add 1 on the power, which is going to be x to the power 2 divided by the total power, which is 4 divided by 2, and we end up having 2x squared as our result, and our upper limit of 0 and lower limit of minus 2. Now we substitute our upper limit into the expression. When we substitute our upper limit in place of our upper limit is 0 in place of x, so we're going to have 0 cubed over 3 plus 2 times 0, which gives us 0. And then we say minus the substitution of the lower limit, which is minus 2. When we substitute minus 2 in place of x, we're going to get minus 2 cubed over 3 plus 2 times minus 2 squared. And when we solve, we're going to have 0 minus 16 over 3, which gives us the result of minus 16 over 3. So the negative that we have on our value, it simply indicates that our area is below the x-axis, but our total area for that field is 16 over 3, but the negative simply signifies that our area is below the x-axis. So when we solve also the area which is above the axis, which is for a squared, we're going to integrate the same function, and then with the upper limit of 2 and the lower limit of 0, which gives us, when we integrate x cubed, you are going to get x squared, you are going to get x cubed divided by 3 plus 2x squared with the upper limit of 2 and lower limit of 0. Now substitute our upper limit, which is 2. When we substitute our upper limit, which is 2, we are going to get 2 cubed divided by 3 plus 2 times 2 squared minus now substitution of the lower limit in the same expression. When you substitute the lower limit, you are going to have 0 cubed divided by 3 plus 2 times 0 squared, which gives us, when you solve the first substitution of the upper limit, it gives us 8 over 3 plus 8 minus 0. Then we have 32 divided by 3 minus 0, which gives us the result of 32 over 3. So for us to find the total area for the integration of the whole range, or the total area covered by the graph between the interval of minus 2 to 2, we add the two area, which is area 1 plus area 2. So now our area 1 is 32, which is 32 over 3, which is above the x-axis, and area 2, our area 1, which is below the x-axis, is 16 over 3. So we don't take the negative. The negative is simply signifying or indicating that our area that we calculated is below the x-axis, but the value of the area is 16 over 3. So we take the value of the area, which is 16 over 3, then we add the value of the area for area 2, and we are going to get 16 square units as our total area covered from the range of minus 2 and the range of minus 2 to 2, and below the graph of between the x-axis and the graph of y is equals x squared plus 4x. Let's now look at another method of integration, which is called integration by parts method, which is applied in a complex integration, which is the derivative of product rule. So integration by parts is a special method of integration that is often useful when two functions are multiplied together, but is also helpful in other ways. So the integration by parts method is derived from the power or product rule of integration. So the integration by part method simply says, if we have got the integration of two functions u and v at x, that u and v are representing two functions, then when we are integrating two functions that have got the product of each other with dx, then we can integrate using the product integration by parts method, saying u integration of v dv dx minus integration of derivative of u times integration of v dx. Or we can write it in the form of, if we have got the integration of u dv dx, it means our two functions, which is the function u and v, one of the function will represent it as our as dv dx, and the other function represent it as u dx. So when you have two functions, which is u, and the other function, which is dv dx, when we're integrating using the integration by part methods, we're simply going to have the results of uv minus integration of the function, which is v du dx, du dx, both of them dx. So u is the function ux, and v is the function vx, and u, which is the derivative, is the derivative of the function ux. So the d, when we are finding our v, we need to integrate our dv that we have for us to have the function v, for us to substitute into this function of integration by parts methods. Here is our first example of solving using integration by part methods. Our question is saying integrate x cos x dx. So when we are finding a solution in this expression where we have got two functions multiplying on each other using integration by part methods, we need to consider the expression that is easier to differentiate, to consider it as our u. So in this situation, we have got an expression x and we have got an expression cos x. So we consider u to be our first expression, which is x, since x is easier to differentiate. So we let u is equals to x, and then the second expression, which is cos x, we let it to be our dv dx is equals to cos x. And now, since we have got u is equals to x from our expression, we now have to find our du dx, which is differentiating u in terms of x. So when we're differentiating x, we're going to have a value of 1, which is the derivative of our x. And then on the dv dx, since we have got a dv dx, which is cos x, now this is the derivative. You know that the integration is the reverse of the differentiation, so we need to find our v. So since we have got a dv dx, which is cos x, we need to integrate our dv dx for us to get a v. So when we integrate the function, which is cos x, for our dv dx, which is cos x, we are going to get a sin x as our result of integration of cos x. So sin x is our v. So now we have got a v, we have got a u, we have got a du dx, and we have got a dv dx. We now substitute these values into our integration by parts formula, which says integration of u dv dx is equals to uv minus integration of v du dx. So we know that our u, which is cos x, and cos x is representing our dv dx, which is a dx, which now takes our result as uv. Our result, which is uv, we know that our u is x, so we put x in place of our u, and our v is called sine x, we put sine x in place of our v, and minus integral of v, our v is sine x times du dx, which is 1. Then we say sine x times 1, it gives us sine x. So integral of sine x from our trigonometrical rules of integration of sine x is called cos x. So end up having our final value or final integration solution of x sine x plus constant c, cos x plus constant c as our result of integration of x cos x dx. Let's look at our second example of solving using integration by parts methods. We have the question that is saying find the integral of x exponent x dx. So in this situation, we have got two expressions multiplying on each other with its x and exponent x. So we consider x1, since x is easier to differentiate, so we let u is equals to our expression x, and then we let exponent x to be our dv dx. So our dv dx is equals to exponent x. Now we have got u is equals to x. We need to differentiate to find our du dx. So our du dx is equals to 1, since differentiation of x is equals to 1. And our v, for us to get v, since we have got dv dx, which is on x, we need to integrate our dv dx. Integration of an expression of dv dx, which is integration of exponent x, which it gives us an exponent x. So our v is equals to exponent x. So now, in our integration by parts method, which states that integration of u dv dx is equals to uv minus integration of v du dx. So in place of u, in our formula, we're going to put a value of our u, which is x, and in place of v, we're going to put our value of v, which is exponent x, minus integral of v, our v is equals to exponent x, times du dx. Our du dx is equals to 1, which we integrate in terms of dx. So when we say exponent x times 1, we're going to get exponent x. So we find the integration of exponent x. Integration of exponent x is going to give us exponent x. So end up having a final result of x exponent x minus exponent x plus a constant, which is an arbitrary constant of integration. So this is our final result of the integration of x exponent x dx. Our third example says find the integral of ln x dx. So in this situation, we have got only ln x. So we assume that we have got a 1 that is multiplying also to ln x, then we have got 1 times ln x. So we consider ln x as one function. So we let u is equals to ln x, then we let 1 times ln x. We let the presence of 1 here being our dv dx. So we assume that there is 1 that is multiplying with ln x. So 1, we consider it as our dv dx, and then function ln x, we consider it as our u. So when we differentiate ln x using the logarithm rules of differentiation of logarithms, we know that the differentiation of ln x is equals to 1 over x. So here we've got u is equal to ln x, our du dx is equal to 1 over x, and since we consider our dv dx as 1, for us to get v, we need to integrate our dv dx. So integration of a function of dv dx, which is integration of 1, it gives us a value of x. So now our v is equals to x. So when you substitute these values into the integration by parts formula, which is stated that integration of u dv dx is equals to uv minus integration of v du dx. Our function, which is integration of 1 ln x dx, is equals to, in place of u, we're going to put our value of u, which is ln x, and in place of v, we're going to put our value of v, which is x, and then we're going to have x ln x minus integral of v, our value of v is x, times du dx. Our du dx is equal to 1 over x dx. Now when you say x times 1 over x, x is going to cancel each other, then you end up having only integral of 1 dx. So when you're integrating 1 dx, we're going to get an x. So integration of a constant, which is 1, is going to return a value of x as our result. So end up having our final result as x ln x minus x plus an arbitrary constant, which is c, as the final result of the integration of ln x dx. Here are some exercises to test your knowledge and understanding. Find the integration of each and every question using an appropriate integration rules. Refer to our previous examples that we have worked on in order to understand which rule of integration to apply at each and every question. Now we come to the end of our chapter 5, lecture 2 for integration. Thank you all for being part of RICHFIELD Hybrid Learning Program. I wish to see you all in our next lecture.